Welcome, everyone. I'm Tom Hudson. I'm a senior security engineer here at Bishop Fox. And I want to thank you for joining us today for the 11th episode of our Tool Talk series. We're really excited to have you with us for this series, where our security experts break down tools and research used by offensive security professionals. We look at the origins and technical components of the featured tool, how pen testers can use them to find and exploit vulnerabilities, and how you can use them in your own projects. So while you're with us today, I'll be covering a tool called JSLeuth that I developed recently to extract URLs, secrets, and other interesting bits from JavaScript source code. So without further ado, let's kick off this episode. So I said I'm going to be talking to you about this tool called JSLeuth that I wrote. And to give you an idea of what it is and why I wrote it, I want to talk about the old web. So the old web was pretty easy to crawl, pretty easy for programs to find things on it. Links were links, marquees scrolled across the page, and HTML was generally unsullied by JavaScript. And when JavaScript arrived, mostly it made things look a bit nicer and have fancy animations and effects, or made a trail of kitten GIFs follow your cursor. And HTML kind of looked like this. So this is an example of an anchor tag or a link. And you can see there's an href attribute to /guestbook.html. And that was pretty much the only way to make users navigate from one page to another on a website. And that's pretty easy for programs to deal with. They can extract that path from the attribute, and they can load that page, and they can repeat the process. That's pretty easy to deal with. But then in about 2001 or so, JavaScript got a new thing, a new power. They're pithily named XML HTTP request, or you might have known it as a particular ActiveX object, as it was introduced by Microsoft. And that meant that JavaScript could now fetch new data, new stuff into the page without a page reload. It meant it could do HTTP requests. We fast forward a couple of decades from then, and we have React and Angular and all of these complicated JavaScript frameworks, which is great for us humans. It makes the web substantially more interactive and more fun. But at the same time, it makes it much harder for programs to crawl this new web with JavaScript, with its myriad different ways that it can load new URLs. Now, if you want to deal with that situation and still crawl the new web, as it were, one way you can deal with that is to use a headless browser. So a browser running on a system like a regular browser does, just like you use every day, but with no UI, nothing visible. And instead, we program the behaviors of the browser to make it work. And we can use that to do a sort of dynamic analysis to discover the URLs that are loaded by JavaScript in the regular execution of the page. It's not a perfect solution, though. It's kind of slow, and it's really rather resource intensive, as you'll probably know if you've ever run Google Chrome on a laptop with not much RAM. And the other real big limitation of it is you only find out about things that are actually executed. So if you are trying to control a headless browser to crawl a website, it's really up to you to write code which finds the elements in the page and stimulates them, to find buttons and click on them, to open menus and so on and so forth. And that can be really tricky. And you tend to not end up with particularly good coverage of the JavaScript that is available to the application. A lot of it often goes unexecuted. And that means we don't get to find out about the things that it does. Do a type of static analysis using regular expressions. So regular expressions are good for matching particular patterns in text and extracting data from them. You might have heard there's quite a well-known quote that if you choose regular expressions as a solution to a problem, now you have two problems. And that's perhaps maybe a little bit unfair to regular expressions, but it gives you a good flavor of the kinds of things that you can come across. So an example of a call to the fetch function, which is sort of a modern equivalent of the XML HTTP request that we mentioned before. And the bit we're really interested in here is the path, /API/v2/guestbook. It'd be really useful for us to be able to extract that path and give it to a crawler so that it can then load that page, extract the responses, and repeat. But that can be a little bit tricky using regular expressions. It might seem simple enough at first glance, but you have to deal with things like nested and escaped quotes, differing white space, other random variants. And one of the things I really want to hammer home here is that at scale, when you are crawling many thousands or perhaps hundreds of thousands of web pages, edge cases really become commonplace. Something that happens 0.001% of the time might not seem significant until you have to do it a million times, and then it happens regularly. Also, running several dozen complex regular expressions across today's modern multi-megabyte JavaScript files isn't really great for performance, but perhaps worse than that, maintaining several dozen complex regular expressions can be a real nightmare. And just to give you an example of the kinds of problems you have to solve, we have an example path here: API v2 guestbook with single quotes. We have a regular expression that matches that fine. But if it was with double quotes as well, we have to account for that differently. And then if there's a single quote inside double quotes, we have yet another problem to solve. We have to use these things called back references, where you can see that /1 in the regular expression. And these are, examples for just one small, fairly simple case. But to give you an idea of how really tricky things can get, there's a regular expression at the bottom of this slide, which I stole from another web crawler. And I wouldn't bother suggesting trying to read and understand this, because the point is, it's too complicated. It will have been complicated to write in the first place, but I think even more complicated, more difficult to read and understand, and certainly to maintain and debug. Also, there's the fact that extracting the URLs and paths by themselves is nice. It's useful. But extracting the context around them is even better. So this example we have here is that same call to fetch, but we can see that there's a method of post specified, and there's some headers to be passed along with that request. And from a web crawler's perspective, having the right method and the right headers might be the difference between a request working and not at all, and returning an error that's essentially useless. That becomes a dead end for the crawler. But it turns out we can use the power of a thing called TreeSitter, which is a parsing library, to make this task actually possible and without crazy, ridiculous regular expressions. I want to give a little shout out to Louis Ardern, who gave a talk about static analysis of JavaScript some years ago that I saw. It was very helpful. And also to SemGrep, where Louis actually works these days, that gave me the inspiration to use TreeSitter to solve this problem. So raw JavaScript source code is difficult to understand for humans even, and that's kind of doubly true for programs. That means humans have to write code to understand things. That's generally speaking quite difficult. Now, TreeSitter parses JavaScript and dozens of other languages into these things called syntax trees. And it's meant for tasks like syntax highlighting rather than the execution of the code. And that means it's been built to be tolerant of minor errors, which on something as wide and varied as the web turns out to be really useful for this use case also. And now for the first time, we can actually see the JSLoose tool in use here. JSLoose has a mode called the tree mode that you can use to print a textual representation of the syntax tree as produced by TreeSitter. So here we can see we have a file called hello.js, which contains the traditional hello world program called a console.log. We pass it the string hello world. And we run JSLoose tree and then the file name hello.js. And we can see we have a printout that's describing in great detail and sometimes very verbosely the structure of this program as a tree. We can see there is a program that contains an expression statement that contains a call expression, which has two parts, a function and the arguments. And if we look in there, we can see all the parts, the console, the log, and the hello world. But they're all in this structure that we can easily interrogate and in predictable places where we don't have to care about things like different quoting styles or white space and that kind of thing. So there is a JSLUS Go package as well as a command line tool. But in this session, we're going to focus mainly on the command line tool because that's the way the vast majority of people will probably interact with JSLUS. And I want to start off by showing you the URLs mode. The URLs mode can be used to extract URLs and paths, and also, where possible, the HTTP methods, headers, and body data, that contextual information that surrounds a request. And it can do that for calls to fetch, uses of XML HTTP request, but also assignments to things like document.location or the source attribute of elements. And also some libraries are supported as well. So calls to jQueries, $.get, .post, and .ajax, and a handful of other places too. And we can see an example of how to use the URLs mode here, which we're running against that previous fetch example that we had on the last slide. We can run JSLUS URLs and the file name. And as output, we get some JSON that describes the URL that was found within that fetch call. So we can see the URL is API v2 guestbook, but we can also see the method was extracted, as well as the content type header. And we can see we have a type field here as well, which tells us what type of code, what this URL was being used for, what the context was when we found it, in this case, in a fetch call. So XML HTTP request turns out to be especially annoying to deal with. And I think this is a really good example of where regular expressions would have been a very difficult, if not potentially impossible way to deal with this problem. So here we have an example function called call API that uses XML HTTP request. And the reason XML HTTP request is tricky to deal with is that the data we really want, the path and the method and the headers and so on, are spread out between multiple function calls. So we can see here we have an object called XHR, and we have a .open call, which includes the method and the path that is being called. But then separately, we have two different calls to set request header, used to set the request headers for this particular request. And on the right, you can see the output of JSLUS when run against this code. So firstly, we can see we've extracted the method and the headers, and the type is set to XML HTTP request.open. You can see we've also parsed out the query parameters, that format parameter. But one really interesting thing here is we can see that JSLUS understands string concatenation. So the path passed to xhr.open was actually made up of three things. The string /API/ and then a method variable, and then another string that contained the query string parameters, this format equals JSON part. Now, if we were extracting the path using regular expressions, it's quite likely we would have seen just that first part, just that /API/. And that really doesn't tell us a great deal about what that request should actually look like. But because we have a parse tree available to us, we can see that the second argument to xhr.open is a string concatenation expression. And we can essentially collapse that down into the string you can see on the right, /API/EXPR with the query string in there. Now, this may not be a valid URL, but it is at least in the format that is expected, and we can see quite clearly which part of this path was variable. We didn't miss the format query string parameter, which again might have been the difference between finding a bug on this endpoint and not. And also, we can change that placeholder to be something else. So perhaps the word fuzz, which is the keyword used by tools like FFUF to place items from a word list into the request. So we might be able to use this output straight into the input of a fuzzing tool to find actual working URLs, knowing where the variable parts of that path should be. Now, JSLUS doesn't just deal with URLs, it deals with some other things as well, including secrets. Because modern web apps talk to lots of APIs. They run in the cloud, and you need to use secrets for stuff like that, things like API keys and passwords. And sometimes, occasionally, thanks to rather complicated build processes and so on, those secrets end up in JavaScript files. And that's something that we've seen quite a lot of at Bishop Fox. So we wanted to be able to handle those situations well. And that's why you can find secrets with JSLUS as well. So you can see an example call here. We run JSLUS secrets and then a file name. In this case, this file contains an object that has an AWS access key. This is kind of an interesting choice of example because AWS access keys have quite a useful property, or at least useful to security researchers, which is that they have a common set of prefixes, either IKIA or ASIA or one of a dozen other prefixes, and they have a fairly predictable length and set of characters they use and so on. They're a prime candidate for spotting with regular expressions alone. And I've seen that technique be effective. One of the problems with that, though, is that an AWS key by itself is effectively useless to a pen tester or security researcher. You also really need the associated secret in order to have any kind of impact from discovering that. And it might be that when seeing an AWS key in the result from a regular expression search with a tool like grep, you can go and look at the file and discover if the secret is there yourself. But that's not very useful for automation, having to have a human involved there. The problem with AWS secrets is that they are effectively a random base64 encoded string. And those sorts of things show up all over the place on the web in things that are not secrets. Things like base64 encoded SVG images, for example, might match. But because we have a parse tree, in this case provided by TreeSitter, we are able to look for the predictable pattern of an AWS access key and then essentially climb the syntax tree to find the parent object that contained it and scan through just the values in that same object to look for a secret. Because chances are, if the secret was there, it would probably have been in the same object. And in this case, you can see that we extract the key and the secret, and we put them in a predictable place in JSLUS's output under the data field, under the key and secret field, even though they are not the original key names used in the JavaScript source code they were extracted from. That makes it easy to pass these results on to further automation that might validate that that key is valid or not, and save you time if you're looking at tens of thousands of JavaScript files. We can also see here there's a context field in the output. And that context field is a JSON representation of the object in which the key was found. And we can see that we have some extra keys there. There is a bucket field and a server field. Now, it might be that those values represent some important information. For example, what S3 bucket, for example, this AWS key and secret are used for. And it's those kinds of things that can really save time for human researchers reviewing the results of the tool. So there's built-in matches in JSLUS for AWS, GCP, GitHub, and a few other different types of secrets. Well, the problem, though, is the internet's really awash with many different types of secrets. And it might be that your particular target uses some obscure vendor that we haven't accounted for, or maybe they even have their own homegrown system. They have their own types of secrets that show up on their attack surface from time to time. And it's really important to be able to look for those kinds of things. And as a result, you can provide your own patterns to JSLUS in a JSON file. So we have an example of one of those on the left. We have two matches, as it were, here. One we've called generic secret, which looks for any object key that's a secret, private, or APA key. And then we have a regular expression to run against the value as well. Now, you can match against object keys and the values, but you can also match against just the keys or just the values. And if it's just the values, that will include regular variables as well as strings that are included inside objects. But you can also match entire objects. One of the things I've seen quite a few times that I've wanted to extract from JavaScript files is these Firebase configuration objects that contain an API key, an app ID, and a domain, and a bucket, and a few other things. Now, they're not necessarily a problem by themselves, but they can sometimes point to a Firebase database which is misconfigured. So there's still something I would like to know about from a JavaScript file. And you can see here on the left, we've used the object field to specify a series of other sub-matches to match on that object. So for the first one, we match any key called API key and a value with this particular regular expression. And for the second one, we match against the key only and say any object that has a key of storage bucket, and also a key of API key where the value matches this regular expression, we want to extract the entire object. So you can see on the right, we run jsloosh secrets -- patterns equals custom.json, which is the file we stored the patterns on the left in, and then the file name or file names of the JavaScript file we want to run against. And we can see we extract the entire object, including the keys we were not matching against, so that we get the full context for what we were trying to match against, because the app ID, the author domain, those kinds of things, it's probably information you also want, but you don't necessarily want to match against them. Now, TreeSitter, it turns out, is really quite cool, and it has its own query language for querying syntax trees, and that's what allows jsloosh to do a lot of the things that it can do. We use it to find objects with particular patterns and so on, or calls to particular functions so that we can extract particular arguments to those functions. But jsloosh also exposes this functionality to the user using what we call the query mode. And that lets you run TreeSitter queries against arbitrary JavaScript, but then also massage those results into valid JSON so it's suitable for processing with other tools like JQ or Gron and so on and so forth. And I suggest you use the tree mode we saw earlier to help you write queries that will tell you the names of the types of things you are looking for. But otherwise, I highly recommend reading the using parsers query syntax section of the TreeSitter documentation. So here we have an example of one of the more simple things that we can do with the query mode. So we run jsloosh query and -q followed by the query we want to run, which in this case is the type of thing we want to extract from the source code in brackets, in this case objects. And then a little @m is a little placeholder to tell TreeSitter the thing to the left of that is what we actually want to extract. And then we have the file name. In this case, we're piping to JQ to improve the formatting. Now, we're running this against our previous fetch example that we saw several times already in this presentation. We can see that the full object itself was extracted, and where the value could not be converted directly to JSON, in this case, there was a call to JSON.stringify, we converted that to a string. I want you to notice that the object that was passed to JSON.stringify was still identified as an object and extracted. And we can see that at the bottom of the output. To give you a kind of an idea of the sorts of things you can do with this, I came up with this little one-liner. One-liners seem to be something I'm relatively well known for, so I thought it would be a good thing to include. And the problem we're trying to solve here is that we want a word list for fuzzing APIs, for example. And that means we want to know about all of the different special words that a target uses to refer to things. And in this case, that's the object keys in JavaScript files. So here we use the find command to search the current directory for files, that's -type f, that are named anything.js. And we pass those to jsloosh directly. jsloosh can accept a list of file names either as arguments or as line delimited input on standard in. So we run jsloosh query with that same object query that we saw before. And we pipe that into JQ to turn each object into a series of objects describing the discrete entries within those objects. It's a bit of a mouthful, isn't it? And output those with raw output. So we're extracting just the keys from the objects. We then pass to sort to put them in order, which is a prerequisite for unique -c, which provides a count of how many items exist of a particular type. And then we pass to sort -n for numeric and r for reverse. And that gives us a list of all of the keys used in the JavaScript files that were provided in frequency order. That is to say, the things used most often come first, and that means we're more likely to see success earlier on. This is a really common task for people, pen testers, bug bounty hunters, that kind of thing. So it's really great to be able to do these kinds of tasks. Now, the command line tool is nice, and you can use it for automation in shell scripts and that kind of thing. But it's limited to the use cases that we foresaw and built in. If you want to really get serious and build JSLUS into your own automation, I suggest taking a look at the Go package as well. So it's just a real simple example of how you can use the JSLUS package to add your own custom matches, where rather than just having the functionality exposed by the JSLUS command line tool, you have the full power of TreeSitter at your disposal. So here we create a new JSLUS analyzer in which we pass the source code of the JavaScript we want to analyze. And we call add URL matcher on that analyzer. And in that, we pass in a function which accepts a single JSLUS node or pointer to a JSLUS node as its only argument and returns a JSLUS URL pointer to. And here we do a really simple check. We see if the value of the string that we found starts with mail_to. So JSLUS doesn't extract mail_to links by default, but you can make it do that pretty easily. One of the things I want to draw your attention to here is where we have this val variable being set to n.decoded string. JSLUS understands JavaScript encoded strings with all of the different string escapes that entails, \u, \x, and so on, which is more than is supported in just JSON, for example. And that means that, regardless of any obfuscation techniques or just other bits of random encoding that happen to appear in a URL, we can deal with those situations without a great deal of effort here. So I want to leave you with one last one-liner. And, this is really an answer to a problem, which is sometimes the most interesting things in JavaScript are in inline JavaScript rather than static JavaScript files. And I think that's because with inline JavaScript, you can use server-side languages like PHP to inject dynamic information about API keys and so on, for example, into the JavaScript much more easily. Now, I suggest using a tool called HTMLQ to extract those. And HTMLQ is like JQ, but for HTML. And we can combine that with a little bit of shell trickery to process them. So here we find JavaScript files, or actually HTML files. We find all files within a directory, and we run the file command against them. If you're not familiar with the file command detects what type of file something is, whether it's a JavaScript file, an XML document, HTML document, and so on, and prints the file name followed by a colon and followed by that type. So we can use grep to pull out just the HTML documents, and then we can use cut to remove everything after the file name because it's just the file name we want here. We use a while loop to read that file name into a variable called HTML file. And then for each line, we run JSLUS secrets with this shell substitution bit here. So the less than and the brackets, we run HTMLQ-F, we pass it the file name, tell it to extract the contents of script tags, just the text that is within them. And the output of that command will be effectively replaced by the shell by a file descriptor that contains that code. So this lets us extract all of the contents from inline script tags in a set of HTML documents and run them against JSLUS pretty easily. JSLUS might get some native support for HTML files soon, but for now, it's still something that's totally possible to do. And if you're integrating JSLUS into your program using the Go package, then that's something you can do using any HTML parser that you want. So that's everything I have to tell you about JSLUS, but let's shift gears a little bit, and we have time for just a few questions from the audience. So the first one is, what was your inspiration for creating JSLUS? Oh, that's a really good question. I think the main thing is, we were trying to crawl websites without using headless browsers or the resources required to use a headless browser, and also to extract those bits of code that weren't necessarily being run if we weren't stimulating the page in exactly the right way, or perhaps would never have been run. Maybe the JavaScript for the administration panels of a particular website was being included in the JavaScript bundle. That's something we've seen quite a lot. And when I looked at existing tools to do so, I found that they primarily used regular expressions, and they could be, firstly, quite noisy. But secondly, they would miss things like the query string and the string concatenation example that we had earlier on. So that was the real inspiration for creating this thing in the first place. The next question we have is, what are your future plans for JSluice? So I think the main thing that we'd really like to get working is better support for some of the more popular JavaScript frameworks like React and so on and so forth. You know, they're places where they're not using fetch and XHR and that kind of thing directly, but they have their own abstractions over them. But they're still common abstractions used by many different web applications. So I'm really looking forward to getting better support for those frameworks in JSluice directly. Next question is, why did you use Go to write JSluice? That's a really good question. And I think probably the answer that's maybe a little bit disappointing to hear, but is very true, is Go is the programming language that I'm best at. But it's also one that has a really great standard library, but also a great deal of very useful third-party packages as well. So, for example, there is the Collie crawler package, which works really well with the JSluice Go package, for example. But really, I think the important thing for me is if you have a language that you are the best at, it makes sense to use that language where possible. So thank you so much for joining us today. And if you want to learn more about JSluice and our other BishopFox tools, you should check out our blog posts and our tools page on bishopfox.com. And we would really love to know what you think about this tool talk. So let us know in the chat, and I'll see you next time.